Hello, everyone. My name is Olzhan Bisarinova, and I'm a data scientist at the Institute of Smart Systems and Artificial Intelligence. In this video, I'm going to talk about explainable AI using visual explanations. I will focus on inner mechanics of interpretability methods. How interpretability occurs. We should introduce three basic concepts while we talk about interpretability. One of them is saliency. Saliency refers to unique features such as pixels or resolution of the image in the context of visual processing. Saliency information is further used to create a saliency map. Saliency map is one of the most important concepts because it directly relates how interpretability is being occurred. So saliency map is a topographical representation of these unique features depicting the visually alluring locations in an image. Apart from saliency, there is also another notion called feature maps, which shall also participate in creation of saliency map. Feature maps are generated by applying filters or feature detectors to the input space of the image. On the right-hand side, we can see how feature maps are different from saliency maps and also different saliency map names for different interpretability methods. Let us talk about how saliency map is being formed, as it comes to be the resulting part of the interpretability method. As a first step, we take the visual input and decompose it into a set of topographic feature maps. Combination of this feature map is being provided as an input to the saliency map. Further, we look at how different modalities contribute independently to the saliency map, and the strongest features compete for the saliency. And the maximum of the saliency map defines the most salient image locations. In other words, those locations where we should pay our attention to. Here comes the schematic way of saliency map formation, and as you can see, as a first step, we look at the different features such as colors, intensity, and orientation. Those features further is used to create feature maps. The combination of these feature maps creates saliency map. And at the saliency map, we look at the most salient regions which participated in the prediction process inside a neural network. Interpretability methods can be categorized into three large groups. One of them is backpropagation method, another one is activation-based method, and the third one is perturbation-based methods. As the name suggests, backpropagation methods rely on the backpropagation process inside the neural network, how gradients has been calculated during the backpropagation process, and this gradient calculation is being used to compute the confidence score for explaining the generation. First, we have activation-based methods, and they calculate the weighted linear summation of the last convolutional feature maps, and thus we will be able to visualize the model decision. Perturbation-based methods deals with the input space, and by manipulating the input space with methods such as blocking, blurring, or masking, we can see how differences we made to the input space can develop the saliency map. Let us have a look how interpretability method has been evolved over the time. And as we mentioned, first one of the methods which has been suggested first is gradient methods, and in the gradient methods we see how change in input space dimension would change the prediction in neighborhood around the input. Integrated method, gradients and gradient star input method is a variations of the gradient method. And in integrated gradient method, we also look at how the prediction output has been changed with respect to features of the input. And in relation with the output, we look at the difference between the attributes that sum up to the target and the target itself. Gradient star method is being applied on top of the deep neural network predictions, and we also enhance the results by multiplying the gradient with the input signal. Guided backpropagation execute the replacement of maximum layers by convolutional layer with increased stride. The convolution method maps feature activity in intermediate layers back to the feature space, and thus we can see how which input patterns caused the activation. Another method which has been popular for a while is the class activation maps. Here we first create a feature vector by concatenating the averages of activations of convolutional feature maps, which are located before the final output layer. And then a weighted sum of these vectors is fed into the final softmax layer, and we then project back the weight of the output layer on the convolutional feature maps. so thus we can identify the important image regions. Grad-CAM is a strict generalization of CAM, and it uses class-specific gradient information, which flows into the final convolutional layer of CNNs, and it produces coarse localization map of the important region in the image. Grad-CAM++ introduces the effect of high-order gradients with inclusive only to positive elements. So the different feature of gradient CAM++ is then we'll be able to identify multiple object instances in a single image, which didn't exist in the previous interpretability methods. To see how these interpretability methods are different from each other, we can look at the visualizations of them. Some of them has been introduced. We can see how these interpretability actually work in action using the ImageNet sample images in the investigate package. At the moment, this interpretability methods is being continued to evolve, and we already introduced Grad-CAM and Grad-CAM++. Since then, there has been introduced also a score-CAM, and one of the latest methods which available and considered to be state-of-the-art is called Relevance-CAM. So what is the working principles of Relevance-CAM and why it's better than its previous counterparts? It utilizes layer-wise relevance propagation to obtain the weighting components. This is the working principle, and in comparison with previous counterparts, it resolves the shattered gradient problem, which were causing noisy saliency map for intermediate layers. So also it analyzes not only the last convolutional layer as it occurs to most of the previous method, but it also takes into account intermediate layers as well. So let us look at how it works, like in terms of the schema. We first create activation maps, which are extracted during the forward propagation. And we also have relevance maps, which are calculated by relevance propagation process. Relevance weighted class activation maps is further then combined to create the saliency map. And from the saliency map, we can see visually alerting locations which are important in decision. Let us also have a look how the score has been calculated to obtain the highest saliency regions. So here comes the formula where alpha k is a weighting component calculated by global average pooling of the relevance map. The relevance map is being denoted R subscript k, and it denotes the relevance map of the i's layer feature map k for the target class C that can be obtained through the layer-wise relevance propagation. Here comes the examples of Relevance-CAM interpretability method, and we can see how Relevance-CAM has highlighted those regions of the image which participated in final decision making of the neural networks. As I mentioned before, Relevance-CAM also shows us how decisions is being made at each layer of neural network. It also can identify several instances of the same object in the image. And here we come to the end of our presentation. This is the literature which has been used in creating this video. Thank you for your attention.